Good afternoon, everyone. I'm Sujatra Bhattacharyya, first year PhD student. I'm working under Professor Arindam Chakraborty. And today my talk is on the influence of the Western Pacific subtropical high on the Indian summer monsoon. So what is the West Pacific subtropical high? It is nothing but, as the name suggests, that it is in the Western Pacific, there in the subtropical zone. There is a high pressure system that is an anticyclone. A surface anticyclone can be seen. The red arrows represent that. I have captured it from Windy. And it is very important, this warm, moist laden winds, which goes towards the South Korea or towards the Eastern Asian part, gives good rainfall, and which they call as the East Asian summer monsoon. Now, there are actually, first of all, how to quantify this Western Pacific subtropical high and how these variabilities can be measured. So first of all, there are actually two kind of variability. One is the interdecadal variations. Another is the interannual variations. So if we see towards just below the interannual variations, there is a figure which represents the WPSHI, the West Pacific Subtropical High Index, which is the quantity to measure the interannual variability. So it is defined as the boreal summer, June, July, August, 850 hectopascals geopotential height anomaly, averaged over 15 to 25 north and 115 to 150 east. But in case of interdecadal variations, Matsumura et al. 2016 showed that this particular zone is not, this conventional definition of this Western Pacific Subtropical High Index, which is averaged over this zone, is not good for this interdecadal variations, because for long-term variations, the variability is not quite high over this region, but it is quite high over this Western Pacific Subtropical High Index, which they have defined over 25 to 35 north and 140 to 170 east. So this red color represents that Western Pacific Subtropical High Index with 11-year running mean. And this gray shaded color, this represents the June, July, August PDO index. So that is also 11-year running mean. So we can see that there is some kind of relation between this PDO, the June, July, August, or the summer PDO index, and this West Pacific Subtropical High Index, which is defined by them for the interdecadal variations. So I will be talking more about these interannual variations, which are governed by ENSO and the atmospheric interactions, following the paper of Huang et al. 2018 and Wang et al. 2013. So this is the West Pacific Subtropical High Index normalized. And this is the variability which is shown here. Now, to understand the variability of this West Pacific Subtropical High Index, the leading modes are first means they turn towards the leading modes of variability of this 850 hectopascals geopotential height anomaly. So what they say is that this is the leading mode, the first leading mode, which captures a variance about 31.2%. And the second leading mode is capturing about 25.1% of the total variability of that WPSHI. So here we can see that these are some warm or some positive geopotential height anomaly over 850 hectopascals, and its correlation with precipitation all over this region is shown. So we can see that in the eastern central part, there is a strong negative correlation which is present. And the positive correlations can be seen, some negative correlations is present, and these positive correlations shown by these green shades are there. Now, its corresponding correlated sea surface temperature anomalies are shown over this region. So, and the 850 hectopascals wind anomalies are also shown. Now, what we can see that this Western North Pacific, this region, as the northeasterly winds, say that these are the anomalies of the 850 hectopascals wind. And if we see the climatology as well, so that also is northeasterly over this region. So it is favoring these winds over these areas. So strengthened northeasterlies results into evaporative cooling over this region. And that's why there is a strong West-North Pacific cooling. And that West-North Pacific cooling results into suppressed convection and result into descending Rossby waves, which further intensifies this West Pacific subtropical high. On the other hand, in this region, if we come, the mean monsoon winds are westerlies, but it will be slowed down because there is a high pressure region which is present over this region. So this cross-equatorial jet, the cross-equatorial monsoon jets which are flows over these areas, these are not only the function of this meridional pressure gradient, but also over this high pressure which is present here will weaken these monsoon winds, and as a result, the evaporitic cooling will be weaker, and the North Indian Ocean temperature, sea surface temperature anomaly will go up. Is positive. Now, this sea surface temperature anomaly, when it goes up, it will have an atmospheric Kelvin wave response, which further intensifies this West Pacific subtropical high. Now, this is all about the leading mode of variability. Now, coming to the second leading mode, we can see that some lows of geopotential height anomalies are over these areas, and there is a strong correlation with precipitation of the second leading mode of WPSHI mostly over the India, which was not in this case. And there is, if we see the sea surface temperature anomalies corresponding to this EOF, then we can see that there is a strong central Pacific cooling which is present. Now, if you see the principal component 1 and principal component 2 corresponding to that EOF1 and EOF2, and 13 years running correlation is taken with WPSHI, we see that after 2000, this is a demarcation which I have made, after 2000 means post 1999, if you say, that there is a strong increase, there's a significantly strong increase in the correlation between the PC2 and the WPSHI, which gives an idea that the second leading mode of variability for the entire period, says from 1979 to 2016, is nothing but dominant in the post 2000 period. But earlier, the PC1 was dominant. This dashed line represents the 95% confidence level. Now, this is as the demarcation was made from before that demarcation, it is that 1979 to 1999, that is the pre-epoch, and this is the post-epoch from 2000 to 2016. So this is the pre-epoch conditions. Again, these geopotential height anomalies are drawn over here, and its correlation is taken with the precipitation. So again, we can see that there is a strong negative anomaly towards the east or this region, but mostly over the Indian region, there is not very strong correlation which are present. Significant correlations are not present. Over the maritime continent, there is some correlations which are present. And obviously, there will be a strong negative correlation because there is a high which is present over these areas. Now, in the post-epoch, we can see that the lows are again coming here. Correlation with precipitation over the Indian region has increased and extending up to the maritime continent region, which is quite similar to that this post-epoch. This picture is quite similar to that of the second leading mode of variability, which I have shown earlier here. So it is quite similar. And the pre-epoch mode is quite similar to this. This thing is also there, the strong negative correlation which is present. So that's why we can conclude that from in the pre-epoch, the EOF1, that is for the entire period from 1979 to 2016, the EOF1 which is present, that is dominant in the pre-epoch, but whereas in the post-epoch, the second leading mode for the entire period is dominant. Now, correlations of the pre and the post-epoch of ISMRI with WPSHI. This ISMRI is defined over the 10 to 30 north and 72 to 85 east, perfectly over that Indian land region. And this Indian summer monsoon rainfall index in the pre-epoch with WPSHI correlation is very, very low. But in the post-epoch, it significantly increased up to 0.58. Bold represents a 95% confidence level. But why is this sudden increase in the post-epoch? That is what they try to find. And to find that, they did this regression of 850 hectopascals velocity potential, first due to Nino 3.4, and then with WPSHI over 850 hectopascals they have seen. So what they saw is that with respect to Nino 3.4, when the regression is done in the pre-epoch, they saw that if there is a slight increase in the Nino 3.4 over this region, then there is a strong convergence as expected, and these regions have over the maritime continent region has a strong divergence. But in the post-epoch, when again the regression of this velocity potential is seen, slight increase in the Nino 3.4, now there is an extension to the central Pacific zone, and there is an extending part of this anomalies or these velocity potentials from this maritime continent towards this Indian subcontinent and towards the Arabian Sea region. And this is also shown by Krishna Kumar et al. 2006, that there is a shift in the Indo-Pacific water circulation post 1990s. And with WPSHI, when the regression is made, so we have seen that we can see that there is, if we increase the high or if the WPSHI index slightly, then we can see that there is a divergence. Strong divergence is seen over this region, but not very strong convergence is seen over this Indian region. There is nothing, but even in the South Equatorial Indian Ocean also, very little convergence, as which is not there in only. And in the post epoch, again with the WPSHI, when it is regressed, strong divergence is seen over here, but now the convergence is occurring over this Arabian Sea Indian region and also over the maritime continent region. So it suggests that the Indo-Pacific Walker circulation due to associated with this Western Pacific subtropical high has increased in the post period. That is giving the good amount of rainfall, means the monsoon rainfall has increased. This correlation with the ISMR and WPC increased because of this. Now, to explain why is it, again, these modes, this is the UF1 and the UF2 modes are sketched. So UF1 mode represents this WPSH is extended towards this region. And this is what I was explaining, that the Indian monsoon, the mean wind will be weaker. And that's why there is a warming over this region. So not much influence will be made by the WPSH over this Indian region rainfall. But OK, over this eastern region, there may be some strong correlation which is present, because this the cross equatorial winds will turn towards this region, not move further northwards. But if it is somewhat weaker, then it can go over this region and cause good rainfall over this. So there may be precipitation correlation over this, but almost all the entire Indian region will have no effect on this Western Pacific subtropical high. But in the post epoch, what happens is that this WPSH is over here, and there is a Central Pacific cooling, and there is a low which is present extending from maritime continent towards this region. So this is nothing but this is nothing but showing that the Indo-Pacific Walker circulation due to Nino 3.4 has shifted westward, and this Central Pacific cooling will also lead to intensify this WPSH, because there will be off-equatorial anticyclonic shear vorticity, because of which this WPSH will increase. And the regression map shows that the Indo-Pacific Walker circulation due to this associated with WPSH has increased, and they have attributed it with this Indo-Pacific Walker circulation, which is shifting westward. That's why there is an increase in the rainfall. So the main driver is this CP-ENSO mode, which is actually forcing this WPSH and resulting into this strong strengthening in the Indian summer monsoon rainfall in the post epoch. A similar kind of work is there, that is the Central Pacific ENSO mode, which is relating to this Indian summer monsoon rainfall using this Western Pacific subtropical high by Gadgil et al. 2019. This is only for the June rainfall. And this NWTP region is nothing but the Western Pacific subtropical high region, which they have chosen in the previous paper. So the first figure shows the June OLR correlation with the June All India Rainfall Index. There is a strong positive correlation occurring over this region, and also some positive correlation is also there, but this is very weak. But the second figure represents the June OLR correlation with the June ENSO index. But we have to remember here, this ENSO index is negative of Nino 3.4. That's why there is a strong positive correlation with the OLR. So what it represents is that this ENSO index with this NWTP OLR, that is also positively correlated, but not very strong correlation. But what these two figures representing is that the June ENSO is impacting this NWTP OLR, and this NWTP OLR is further intensifying or decreasing or increasing or relating with this Indian summer monsoon rainfall. And it has been found out that whenever there is a Central Pacific El Nino, convection is more over this region. It has been found that 7 out of 9 years there is weakening of this OLR over this region, and weakening of OLR, if occurs over this NWTP region, there is a strong correlation with the rainfall, all India rainfall for the June, and we expect that the rainfall will decrease. And this is El Nino affecting the ISM June rainfall through Western Pacific. The reason for that, what Gadgil et al. Has shown is that they have already proved that in Gadgil et al. 2016 that convection over this NWTP is due to the southward shift of the subtropical jet. And Sajani et al. 2018 has also shown, using this Meteorological Research Institute model, which captures the Asian monsoon variability well, that the inverse relationship of the June rainfall exists between this NWTP and all India rainfall. And not only that, the excess and the deficit of this ISM rainfall in June is particularly due to the difference in the phases of the Rossby waves steered in the jet. Another study by Chakraborty 2019, which covers over similar region. This is that northwest subtropical Pacific region. But this is the asymmetric NWPSI. The NWPSI is the index name which they have given, which he has given. This P represents the sea surface temperature anomaly greater than 1 over this region, and N represents the sea surface temperature anomaly less than -1 over this region. Now this P minus N composite is taken over here, and asymmetric represents that it is unfavorable with the PDO index and the ENSO index. What we can see that in the symmetric case, where it is favorable with PDO and the ENSO index, the sign can be easily seen. That is, if this is the NINO 3.4 case, N minus P composite over this, then P minus N composite over the symmetric case is this connection is there, and there is an opposite trend. So PDO negative trend can be seen over this region. But I will concentrate mostly about this asymmetric NWPSI thing, because it has resulted into the June-July rainfall over Indian monsoon. High variability it has produced. So that's why I will mostly concentrate over this particular asymmetric component. Now, this is the zonal and the meridional wind at 200 hectopascals, the upper troposphere. So what we can see that there is a zonal symmetry in this case of symmetric one. There is a zonal symmetry in this warm sea surface temperature anomaly. What we can see that in the zonal zonal 200 hectopascals wind, there is a strong easterlies, and that is also zonally symmetric, which is present here. And in case of the asymmetric mode, in the meridional wind at 200 hectopascals, we can see that there is a phase shift of the Rossby waves, which can be seen very clearly. And over this, the northern and the north central portion of India, in the upper troposphere, there is a strong negative meridional wind anomaly, which is seen. Northerly wind anomalies can be seen over this region. So this northerly wind anomaly in the upper troposphere represents the upper tropospheric divergence, and that can lead to some rainfall variability. So I have made a flowchart for that. So asymmetric mode P minus N, particularly when the positive is more. So the warm sea surface temperature anomaly over the Northwest Pacific and cold anomaly over the Central Pacific. In that case, the meridional winds at 200 hectopascals shows northerly anomalies over the northern and the central India. As a result of which, there is a divergence in the upper troposphere, and the vertical moist static stability decreases over this region. It is shown, but I have not shown here. And hence the convection increases over the Indian region. So the positive anomalies over this central and the northern India, although some sort of negative anomalies are there, but very little. But in the southern peninsula region, there is some kind of negative anomalies of precipitation can be seen. So the asymmetric P minus N component, which has unfavored mode with the ENSO and the PDO indices, has a much more variability as compared to the symmetric. That's why I've chosen this one. And so in conclusions, I have put the mechanisms which I have discussed. So Huang et al. Shows that particularly in the post-epoch 2000 to 2016, CP INSO is the driving that's this Western Pacific subtropical high, and also shifted the Indo-Pacific Waka circulation westward. Associated with the WPSH, therefore the Indo-Pacific Waka circulation has strengthened, which the regression of the velocity potential at 850 hectopascals is showing. The second mechanism by Gadgil et al. 2019, only for the June rainfall, we can see that in the El Nino years, enhanced convection leads to decrease in OLR over the NWTP, as we have the positive correlation which is there, and 7 out of 9 years it has been seen. As a result, the ISMR in the June decreases. A decrease in the OLR over NWTP is due to the southward migration of the subtropical jet. This is the mechanism. Because of that, this all phenomena occurs. And Chakraborty 2019 shows that for the asymmetric modes, positive years particularly, there is a phase shift in the Rossby waves that brings negative anomalies of the meridional winds over the north and the central India that further enhances the rainfall in the June and the July over those areas. So these are the references which I have taken to complete this presentation. Thank you.
Very nice talk. To summarize key papers. Anyone want to ask any question? Anybody from the chat box? Anyone?
Vishal Shit.
Yeah, thanks for the nice presentation. Are you able to hear?
Yes.
Yeah. So my question is about if the second and third mechanism, the one by Professor Gadgil and the one by Professor Chakravarti, is it different sides of the same coin or they are independent of each other? Has such study been carried out?
That study means I have not read that study, but these are means ultimately the ENSO is ultimately driving that in particularly in the case of the Gadgil et al. 2019, the ENSO is particularly driving the same thing which the Wang et al. Is also showing. And Chakraborty et al. Has taken the sea surface temperature anomaly over this region. So I don't know whether this kind of means a common concept is there or not over this.
I see. I can see that Professor Gadgil is there in the online audience. It would be nice if also Professor Chakravarti can comment on this.
Can you hear? Yeah, you have
Yes.
to come here.
Yes, yes.
I think that, I don't know, because I don't know, as he said, I'm not able to explain that whether Professor Gadgil and this one are same. Hi, Vishal, can you hear?
Yes, I can. Yes.
Okay. But
Hi,
I
hi.
have mostly that the P minus N composites which I have taken, right? Those are independent of N, so many of those, all right? So that was a sort of favorable versus non-favorable. So basically, I wanted to highlight the impact of the North Pacific without the impact of ENSO. But Huang et al. Especially, for example, has shown that the ENSO impacts the North Pacific and that further, right? So
I see.
it is possible that the ENSO can impact on which it does actually to the North Pacific Ocean and changes, but there are independent impacts. I think that both Sulochana's paper and that my work that shows the same thing. Possibly they do even impact independently.
I see, because I saw that, I mean, if the jet is changing a bit of the path, then the Rossby waves that it supports will also have anomalous behavior. So I don't know if in Sulochana's paper a similar spatial signature of Rossby waves will be seen. If that happens, then maybe different mechanisms, either ENSO or non-ENSO here, but the signature will be through Rossby waves then. So I thought maybe some comprehensive picture is possible there. But thanks
That's
for the
right.
answer,
Yeah.
Arindam. Yeah.
You want to put one here? Okay.
Okay. So let's look at the state of the monsoon today. We've already crossed a cumulative rainfall of 306 millimeters. Okay, so last week has been extremely good. As most of you must have seen, what's unusual about last week was that essentially the rainfall band, we can't call it anti-season because it's inclined somewhat, is right in the central India for the last 10 days now, 8 days, 9 days. Okay. And so it's been raining like anything in Maharashtra and coastal this one. And so the bad news is Uttar Pradesh, Bihar are not getting any rain, they're well below normal, but central India is doing very well. Now, if you look at the cumulative thing, you can see that entire region covering south except Kerala, entire region south and west and even Orissa, either normal or above normal. Only except for Kerala, there are 4 or 5 divisions here right on the Indo-Gangetic plain which are below normal. Okay, so the expectation is that of course the system will move north in the next few weeks. If it does, it might take care of that region. Now, I saw a very interesting puzzle in the forecast made by, on the top is GFS, bottom is CFS, both with the same initial condition on 8 July. And see the difference. I'm really shocked. So I sent some email to a few people. Nobody has an answer. Why? Remember, GFS, CFS are the same model. GFS uses observed SST or extrapolated. CFS is a coupled model. Okay. Now, for a forecast of 1 week ahead, this is 1 week's forecast. Sorry, this second week's forecast. One would not expect such a large difference in the forecast. So one reason I've been told is because, remember, GFS has a high resolution because the atmospheric model you can run. CFS is a coupled model, so they tend to degrade the resolution. But ironically, in this result, GFS forecast is poor because we are sitting right on 13th July today. It is raining like hell, but GFS is saying right from west coast of India all the way to the Indonesia, rainfall is below normal. So GFS is wrong. Okay. So my only gut feeling is there's some problem in the initialization. Otherwise, I can't explain how atmospheric model at a higher resolution would do poorer than the coupled version of the same model. Remember that. Okay. So this kind of thing is very interesting to understand. I hope more insight will come from people at IITM and IMD, but why this unusual difference occurred. But I can tell you, this is a hint. As a matter of fact, we'll see next week. By the time next week comes, that low rainfall zone that is wrongly predicted may turn out to be right. So essentially, there are various modes in which system is oscillating, and GFS tended to predict that to happen early. And actually, I think in the next week, you'll see there will be decline in rainfall as they come to the end of July. And this kind of north, west, southeast orientation that you see here might be seen, not this week, but next week. Now, this is just the rainfall. And normally you can see that all of July rainfall has been above normal. And if you look at the 2nd July initial condition, it didn't do too well in the last few days. Last few days, rainfall exceeded 14-15 millimeters. And the 2nd July initial condition did not very well. But if you look at the 8th July, slightly better. Still, it does not correctly forecast today's rain. It is a little below normal. But what the model says for the next 10 days is that it will decline slightly on 16, 17, and 18, and then pick up the next 1 week. So that mode I talked about, according to GFS, will not be there. Actually, I must warn you, these are based on 13 July, but that was based on 8 July, that forecast. So the forecast has changed as the initial condition changed. Now let's look at the state of the MJO, which is always relevant to our discussion. And so the MJO today is showing a large divergence in the 200 millibar level, covering parts of India. So India is still favorable for lower level convergence, but within a week's time, the MJO is moving to the east, and India is already in a neutral state. But as you go to 21st of July to 27th of July, the second week, we see India is going to come over upper level convergence, which is not good news, which means the monsoon will decline. Okay, but there is a question mark. On the right is the strength of the MJO as given by Liu from SUNY Stony Brook. He's showing that MJO is getting weaker in the last few days. So if the MJO is weak, it will have no impact on the monsoon. Okay? As a matter of fact, this is a very nice example to show that you can see very clearly that before the monsoon onset, MJO is very strong. Okay, 1.5. One is your typical criteria. But as soon as the monsoon occurred and monsoon becomes strong, MGO becomes weak. The MGO is weakening. So the MGO becomes really weak, then monsoon may not be affected by it. Now, state of the Nino 3.4, it is weakening. It is minus 2.6 this week. But I think it's not going to go to 0 or above. But it is steadily becoming weaker, the La Nina. And the most interesting thing is IOD, which I want Vinay to look at. IOD suddenly plunged to minus 1.14. Okay, that's really surprising. But remember, in my view, IOD responds to the monsoon very strongly. So we have to figure out what is it. But let me show you the actual SH anomalies. This is the SH anomaly about, I think, around 10th of July. The date is not here. You can see clearly in the Arabian Sea, there's a very strong cooling, about 1 degree cooling. Okay, the Western Arabian Sea, because of strong jet. Jet is very strong now. It's about 6 meters per second stronger than 15 days ago. Okay, and the jet is strong, of course, it cools. So that is the what is giving you. But there's also some warm. Sorry, what happened? That should go okay. Sorry. Yeah, I'll move that. Yeah. So I'm trying to connect the IOD and Nino 3.4 to the spatial pattern of the SH anomaly. You can see clearly that the SH anomaly highly negative here, slightly positive here, but not that much. So which is contributing, this is all the contributing more, right? Obviously, than this.
There is no clear IOD pattern in this figure because the Western Arabian Sea cooling is normal. That's a response to cooling.
Yeah.
If we have to have a positive IOD signal, we have to have cooling, or it's a negative IOD, we have to have warming. And more importantly, there should be the difference in the anomalies between east and west. Now, from this figure, it looks like both the western box and the eastern box have the same kind of anomaly.
Here.
Yes.
Okay.
Yeah.
No, but here it's opposite.
No, along the equator.
Along the equator. Okay.
Right.
Okay. It's like sipping in, but you're right.
Yeah, so I would say the IOD is very weak in.
Okay.
Word, right? So it takes 7, 90 to 110. It's much longer than this. Most of the eastern box is cold.
Yeah, but there is no difference in the size.
You're talking about this, right?
Yeah, or even to the much bigger east.
It is uniform. So if you look at the index during this time, it would be very weak.
Okay. Anyway, let's watch next week. Let's see how it goes. Now, this is the Pacific region. And again, Pacific is very interesting this year because very strong negative but along the equator, the tropical instability waves are still playing a role. So they are not given up. That's why your Nino 3.4, which is based on averaging over this region, is showing a decline. But just below that, around, I would say, 5,000 beyond it, very, very cold. So this will also play a role. Okay. And along the equator, the waves are contributing it. Now, let's see what is the forecast from GFS ensemble forecast for 12 to 19, that is this week and next week. Okay. Now, what it is showing is very interesting. It's showing that up to 19 July, which is another 6 days, rain will continue to be very strong here and not so good here. Okay. But the week after, this thing shifts to the Himalayan foothills. So the very large deficit that you see in Uttar Pradesh, Bihar, and Jharkhand will disappear about 1 week from now. That's what is the forecast from ensemble GFS. And then I just want to always show you one example of a good forecast. This is what I saw in BBC forecast for rainfall where you came out of it. This is for today at 12 o'clock. Okay. This is the satellite data. I'm quite impressed. Look at this, slightly shifted, but it is there. This is very much part of this. And this is also there here. Okay. Now, of course, along the western coast, there's a lot of rain, but satellite Polar will not capture that because this is orographic rain. So you won't see that clearly. But otherwise, the three centers of action at 12 o'clock today is what was predicted by UK Met Office 3 days ago. So that's quite good prediction. Now, what's the forecast by GFS and NC1WF? You can see that this is what is this week. So it came out right. We are right in the middle of this system. And next week, this weakens a little bit and there's a strong negative anomaly over northeast. And then it slightly picks up, I think, more north. That's what they're saying. And this ends up slightly different color, unfortunately. But you will see that the features are quite similar. Okay. Now let's look at this is a more detailed forecast, subdivision wise, and it says that this week, of course, everything is right here. This is normal, interestingly, and then the next week it is showing again northeast below normal, and of course south will be below normal. That is till 21st July. Then you go further to 22nd July to 28th July, and up to the beginning of August, we are start seeing declining rainfall over southern India, but mostly it's normal. So it's not saying there's any chance of any break here. It was well above normal this week. It will be normal next week, the week after, and so on. If all this is true, then the July rainfall will be above normal, most probably, if this continues on. Because remember, till the 13th of July, the all India rainfall was 35% above normal. That's a huge increase. Now, I just want to make a point. We all keep talking about La Nina and El Nino, but I wanted to remind you that if you correlate the Nino 3.4 May with the seasonal mean rainfall, the correlation is minus 0.19. Very poor. It's not significant by any means. So we cannot use the conditions before the monsoon of the East Pacific to decide what will happen. But if you look at the correlation between October, 3.4 and Indian monsoon, it's minus 0.54. Very nice correlations. All this says is it is not ENSO which controls the monsoon. It's monsoon which controls the ENSO. Okay. But still, all of us are lazy. We all keep talking about El Nino impact on the monsoon. There is no impact. But the best way to understand this is all of you do research how to keep thinking about it. It is what Webster called long term back. It's a mutually interacting system. So during this period of the monsoon, the ocean and the atmosphere are working together. You cannot separate it. You cannot say ENSO causes monsoon or monsoon affects ENSO. They work together. Okay? So in the language of climate change, global warming, there are feedbacks on both directions. So when monsoon becomes very strong, like this week, it has an effect on the surface winds over the equatorial Pacific. Okay? That changes the way El Nino, the SHE evolves there. Okay? That evolution affects the monsoon further. And they work together over a period of 4 months. But I have not seen anybody really show that nicely. There's a great, it's a tough problem, but it's worth seeing whether in a model one can follow these feedbacks between Pacific Ocean and the Indian monsoon on a weekly or a bi-weekly or a monthly basis to see how the correlation goes from minus 0.19 to minus 0.54. Okay? So that's a point I've not seen anybody talk about, although Webster had a nice review article arguing that one cannot talk about ENSO affecting monsoon, monsoon affecting ENSO, they work together in a mutually interacting system. But he also has not really shown how the interactions are occurring. It can occur only through the surface wind over the Pacific. That's the main link there. So somebody can look at a coupled model simulation and see whether they can follow through this interaction. Okay, last week I discussed this connection between June, July rainfall and the seasonal mean. Somebody asked some questions, so I got one more figure there. This is what I want to show you is, although the line is roughly linear, lots of scattered, but there are unusual years here. These are the years, mostly La Nina, when in spite of June, July being below normal, the final rainfall was above normal. Okay, so those things happen again here. In spite of rainfall being above 450, you can have below normal rainfall. No, most of them are El Nino. These are actually I want you to attention to 2 years, 1913 and 1920. By the way, red means 21st century and green is 20th century. Now, 13 and 20 interesting because in 13, JJAS was not El Nino, but December was El Nino. Okay? That December. So it is the failure of the Indian monsoon that caused El Nino, but and 2020 was 1920 very interesting. There was the El Nino in the beginning of the year. Okay. Now, only problem I have with this is that remember, ask yourself who measured the sea surface temperature in 1920? Nobody measured it. Remember, there are no. Today we have a beautiful set of measurements all along the equator. At that time, there's nothing. That based on a few ship measurements, and in 1939-20, I don't know how many ships went along that Pacific equator. I doubt it. Maybe a few ships involved in trade and other things. But people have reconstructed that based on EUF and so on. But those are suspect, can't be too sure. So I would argue those who are doing research, the most reliable data we have of SST over the Pacific Ocean is in the satellite era, because satellite gives you global picture. Before that, you can look at the data. We have to because we have no choice, but be very careful about whether those SSTs, how many observations are there in the 1920s for you to be able to say precisely a La Nina or El Nino appear. That you have to be careful about. Yeah, 2019 again, I want to show clearly how it appears way on top here. The August, September rainfall. Okay, the same thing I've done from bar chart just to make a point that if the June, July rainfall is below 400, you have chances of getting very low rainfall below 700 or drought. Both are very high. And there's one case I know where it exceeds 800 by a small amount. So if the JJ below 400, very good chance you're going to have a drought. Okay? But as soon as they go into 400, 450, you still have a chance of a drought. 8 years is the number of years. 14 years are here, 30 years. You can see that you can add up 27, 35. So 8 out of 35 chance of a drought is still there. But as soon as you go to 450 to 500, which is above normal for June, July, the chances of drought is pretty low. Only 2 out of 46. So this is where you want to be. This year, one should be hoping that June, July be above 450. Then we are pretty much on a safe ground. So I'm sure that people are going to use this kind of information to advise the government around the end of July whether this should be drought or not, because this is quite reliable, purely climatological data. Okay, but you can see a very interesting case. If the rainfall is above 500 in June, July, the yellow, you'll get either around normal or well above normal. Okay, but most interestingly, when the June are above 550, I see no cases of rainfall above 1000. So although June, July has an impact on August, September, it is not guaranteed it will always help. Okay, so this is worth looking at for understanding how the early water monsoon affects the later part. Okay, well, I think that I'll stop here. So if there are any questions, you're welcome.
JS, I have a kind of a comment.
Yes.
I mean, if I remember correctly about the causality, because Sika always used to say that, the monsoon causes the ENSO. I mean, it is strongly done that way. Like usually,
Ah.
if you have a monsoon failure, then it starts ENSO kind of gets weak. I mean, it kind of causes the ENSO.
Yeah.
And the other one is, I remember there is a paper on causality between ENSO and Indian monsoon. I
Ah.
don't remember it, but I think Ashwin knows that. In case he's there, he can also tell us that
Ah.
where it, this one arrow of causality is very clear that it's the ENSO which causes monsoon. I mean, ENSO causes a decreasing monsoon. This is what that paper. I don't remember the reference.
Yeah, you're right. Ravi, I remember the paper. That paper is written by somebody who does the so-called Granger causality. Okay.
Yeah, that's right.
Yeah. So that paper clearly shows that it is the monsoon linked to ENSO is much more clear than ENSO on monsoon. Yes, it shows that clearly. Although it requires some good background in maths to understand that paper. So essentially, I tell you why the paper unnecessarily complicated. He has done lead lag. That's all he has done. But put it in very fancy language. One of the authors is the Granger name is very famous because he's a Nobel laureate in economics. Okay, so everybody quotes him. But if you look carefully, it is nothing but lead lag. So he does a lead lag between ENSO and monsoon and shows that the highest correlation is when monsoon leads ENSO, not vice versa. Yeah, that paper is good, but not easy to follow. Yeah.
Thanks.
By McFadden, who showed that after that epoch study, there were westerly wind bursts. So he had tracked the westerly wind bursts and showed that many of those westerly wind bursts originate from the central part of the equatorial ocean.
Oh.
And then they have signature over the Western Pacific, which is the which is the main reason for the warmer system of it.
Okay.
Yeah.
Yeah. You know the paper when was it published?
I have to look up it.
Yeah, please send it. So that, I mean, it's good. If many of us missed it, please send the paper. Everyone has sent to me, I'll pass it on to everyone. So sometimes we miss out on some good papers. Okay. Yeah. Anybody else? Yeah.
Slightly, it is possible, but then if it is always impacting ENSO, then the theory of ENSO rising from the ocean, especially subsurface anomalies, are invalid, right? We don't need them, the subsurface temperature anomalies, because definitely subsurface temperature anomalies can't impact the rainfall without changing the surface temperature.
Yeah, surface temperature.
The development of an El Nino requires a subsurface temperature anomaly, right?
Yeah, but that is driven by evaporation anomaly, right?
No, but
The winds.
that's a subsurface.
Yeah.
The
Yeah.
It has a long time scale,
Yeah.
right? So if, I'm not saying there is no feedback, I'm saying that if it has to be one dimensional anyway.
Yeah, but all I'm curious, I'll tell you why I'm saying this. One of you can do this. Run a model in which the monsoon is fixed. Put a climatological rainfall over India and see how the ENSO responds to it. That's the only way to. I don't say, again, maybe there's a paper, I've not seen it. Imagine a model in which the rainfall over India or whole world can be what you call climatological cycle. Okay, seasonal cycle is there, but fixed. And run a couple models and see how the ocean responds. Will you get a different kind of course, there will be an ENSO, but will it be different from what we are saying today? Will it be more regular, for example? Right? Has anybody done that? Somebody must have done it.
No.
So it's what purely from model perspective to understand how much fluctuations in the rainfall over India have an impact on ENSO. You're right. Obviously, ENSO exists independent of monsoon. It has its own, after all, it's an ocean-driven phenomena for a large ocean. I mean, it doesn't require, but Indian monsoon perturbs it. The question is how much, but observation cannot answer it. I don't think you can do that. But a model can give some answer. If the model is good, suppose there's a model which correctly reproduces the ENSO, then that model, you fix the monsoon rainfall to be same every year, give a seasonal cycle, and then see what happens to the ENSO. Is it different? So if there's any paper of that kind, we should discuss that. Okay. So there's no other, thank you. And next week it is.
Yes.
Huh?
Yes.
Yeah.
Can I make a comment on the previous talk? I'm sorry to change the topic. This is
Oh.
Sujatra. Can you hear me?
Sure.
This is on the previous paper. I'm
Yeah.
sorry I couldn't participate in the discussion on our paper and Arindam's paper because
Okay.
I was on a computer without a speaker. Now I'm on one with a speaker. I have joined again. And
Okay.
all I wanted to say was, like Arindam said, now what I understand is, although as we showed in our paper that the NWTP convection is related to El Nino, that paper was meant as an answer to the question, was the June 2014 deficit, could that be attributed to El Nino? And so we specifically looked at El Nino and concluded that it could be. But we have had experience since then. And as a matter of fact, I don't think we need El Nino to get that kind of relationship. What really is critical is the difference in the subtropical jet phase, which is what Sajni and others have shown very clearly, and we had also shown. And so, as Arindam said, he doesn't believe it has much to do with El Nino La Nina. I think there is an element there which can be triggered by El Nino, but the critical thing is to understand what determines the phase of that subtropical jet. And it could be El Nino, it could be other things as well. So this is, in fact, on a shorter period, we see it in many years. Like this year in June, we saw very clearly a signature of the NWTP flaring up. So I just wanted to mention this, that the link between the flaring up of Northwest Tropical Pacific, convection, and deficit in monsoon rainfall is there in many, many June months and not necessarily linked totally only to El Nino La Nina. Thank you.
Okay. Thank you. Yeah. So next week we have Rajat Masiwal is here. Okay. Thank you.